I have a new MemoryWriter 6040 word processor from 1987, but you all knew that because you saw my last video. Well, while I was fiddling with it, this happened. So let's take a look at that floppy drive on the bench. So the first thing to do, of course, is to get at the drive. I have opened this before. So yeah, this should not be a long video. Most likely all that's happened is that one of the belts has gone. However, this is a self-ejecting floppy drive. You don't push the button to eject the disk. The computer operates a motor and that does it. And I've only ever seen these on Apple Macs and Sun workstations, so it'll be interesting to take a look at this. The mechanism which has failed is, in fact, the eject mechanism. So here's the drive, and I can already see a few interesting features. One of which is that it uses the standard connector for a floppy drive, which is a 34-pin IDC connector, except that floppy drives normally have a separate connector for the power, which goes here. And this is getting its power from the floppy drive cable, so it can't be the standard pinout. Not to mention that the eject mechanism needs to be connected up as well. The other thing might be a little hard to spot, but these surface mount components are mostly cylindrical rather than cuboid. I know this floppy drive probably dates to 1987, the same vintage as the rest of the machine. And I know surface mount stuff was around before then. So I wonder what was going on here. I've never seen these before. But the stuff I want is on the other side, so let's just spudge open this protective case and see what's inside. It looks like a floppy drive. This looks very much like the other floppy drives I've seen. On this side, this is a PCB mounted motor for running the spindle, and in there is the flywheel. This is a stepper motor to move the head forwards and backwards. This is new. This must be the motor to operate the eject mechanism, and that's the thing that's failed. Because the spindle motor is PCB mounted, there is no belt there. It's a direct drive, this to the spindle, which is under here. So whatever's gone wrong is over here. Now I do want to be careful because I have wrecked floppy drives by removing the wrong screw. There's some subtle calibration in the position of the head, and if that goes wrong, it's a job trying to fix it. So I think this is pretty much the same mechanism as any other 3.5-inch drive. If I insert a disc, then this thing here slides the hatch open, and then when it goes all the way in, the head's clamped down onto the magnetic media inside. And in fact, here, this is where the eject button would go. So, how is the mechanized thing working? There are gears in there. This module here seems to be the whole eject mechanism. So will it come off? Not with that screwdriver. So, what do we see? Yeah, that's quite interesting. The motor clearly winds this cog around. This has a projection here that sticks down here into this thing. If I insert the disc, see that moves back? That's attached to the eject button. So if I pull here, the disc ejects. And in fact, it's directly attached. So why isn't it operating the mechanism. It looks like the motor is just clipped in, so I might be able to just unclip it. And I can immediately see that while this thing has a cog, there is nothing in here for the cog to actually connect to. So I think that a little plastic gear inside has stripped its plastic. Do I dare try to unclip this back plate, or will something go sproing and it'll lose cogs all over the place? This is awkward. I need to push the clip back and push the plate up at the same time. There we go. And that reveals gears. And I can see the precise problem. So hopefully this one should just lift off. It does. This gear has stripped. You can see the gap here where the teeth should go. Oh boy, what am I going to do to fix that? In fact, if I push the motor back up, there you can see it meshing with the motor. So keep turning the motor, and now it doesn't turn the cog anymore. Let's make a gear wheel. What you're looking at here is the gear which I've scanned on my flatbed scanner, which is a very old trick for getting high resolution images of things. You may notice that there are fewer teeth on this than there were previously, because this thing is falling apart and just handling it made some of the teeth fall off. In fact, after I scanned it, the whole thing broke into 3 pieces, so that's nice. So what I'm going to do is rotate this I put the origin in the center here, and I am going to rotate it until the teeth are more or less horizontal. Let's turn on some guides like so. That will do. Okay, because this will then allow me to crop it fairly tightly to the edges of the teeth. This gives me the outer diameter of the wheel, like so, and commit. Okay, and this is giving me an image which is 440 by 437, which is good enough. Now, I scanned this at 1200 dpi. So 1200 dots per inch in millimeters is 47.24. Therefore, 440 pixels is 9.32 millimeters across. Save, and let's go over to our 3D modeler. My favorite 3D modeler is this one called Solvespace, which is a parametric editor. So what I'm going to do is load the image like so. Now, just calculated somewhere inside the mass of logs, 9.322 is the diameter of the cogwheel, so I can stick a constraint here of 9.322 like so, and we now have our image of the gear wheel at the correct scale on our work surface. So we actually want to put this up near the origin. Because we've got the constraint here, I now cannot resize the thing, but I can grab a corner and rotate it, which is not particularly what we want. So I'm going to stick a construction line. Actually, I don't need a construction line there. If I stick another constraint on these 2 points to say that they need to be horizontal, the thing is now square. So I am going to put a construction line here. between this corner and this corner. And I'm going to create a point, and that point is going to go in the middle of our box here. This is close enough to the center of the gear wheel, so I can now put another constraint to say that these two should be on top of each other, and now we have our image locked at the center of our workspace. So let's draw a few circles to give us the sizes of things, and they're all centered in the middle. So we have this inner circle here, which is the spindle around which the thing rotates. So we put that there, and we actually want this to be a construction circle, so I've put it into green. This means it won't contribute geometry to the model. And let's put another circle here, again construction, and another circle here for the outside of the teeth. And in fact, our outer circle diameter is going to be the same as the diameter of our cog that we know is 0.93 centimeters across. In fact, I cannot put a constraint to say the outer circle has to be the same size as this, because this doesn't have a line on it, but I can draw a construction line from here to here. And now I should be able to say that and that. Nah, I can't say that they're the same. So instead, I'm going to have to do this a slightly different way. If I now stick a point on the circle here and a point on the circle here, and also say that these points need to be on this diameter line, like so, I can then draw an additional construction line between here and here. Select that, and now I can make that the same size as this line. Right, now everything has gone red because there are conflicting constraints, because I still have this constraint here for the diameter. So if I delete that, and if everything goes back the way it was, and you notice that our circle here is actually overlapping the edges of our image, because the image is not quite square, but it should be close enough. Okay, so we now have a bunch of reference shapes. Oh, there's two more things I need to do. Put a set of construction lines from here to here, and it's automatically put a vertical constraint on that because I drew the line vertically. Maybe to another one from here to here. And in fact, let's get rid of that vertical constraint, because that then allows us to move this line. We'll put it to the middle of that tooth. And we put that to the middle of that tooth. And now I can put a reference angle on. That will tell me what the angle is without putting a constraint, which is 11.75. So that's going to be 12 degrees between teeth. Can I convert that to a non-reference? Toggle reference. There we go. Right, now that's a constraint. So these two lines must be 11.75 degrees apart, and I can actually drag the two like this. So we know that actually wants to be 12, like so. And let's put the vertical constraint back on this line. Actually, no, I'll leave it like that. Okay, so we now have our image, which is just for reference. It's not actually going to have anything to do with our final model, and a bunch of construction lines, which I hope are going to be visible in the screen capture. They are quite thin. Anyway, so the way Solvespace works is that you build your model up in layers. We have here our base layer, which I'm actually going to call, rename, more references. Everything here is a construction line, so this is not going to contribute anything to the final model. We're now going to actually start building stuff. So the way I do that is, here it is in 3D with perspective on, just to make life easier to see. I need to select this and a couple of lines. This will then allow me to create a new work plane, which it's done. So I can refer to my geometry lines in the reference plane. Let's add a actual geometry circle, arbitrary size. There, select it and our reference circle. They are the same size. We now have our first piece of geometry. The second piece of geometry is actually going to be the teeth. Now, these teeth look like involute curves, sort of. My 3D printer is a simple filament printer, and I don't think it's capable of reproducing these accurately. So I'm actually going to do something else and hope it works. So we're going to start here, and I'm going to draw a circle of arc like this. I'm going to draw another circle of arc like this, and I've connected them together. Now I actually want to draw a wedge. Okay, so this inner circle here is wrong. This wants to be another circle of arc. Let's put that there, centered on the origin. This wants to be on this line. This wants to be on this line. And the diameter wants to be the same as this reference circle. So we now have our center there. We can now draw real lines from there to there, and from there to there. So we now have more or less an enclosed shape. It's not quite right because of this position here. Yeah, let's actually get rid of those and do something slightly different. So instead, I am going to make a piece of arc there that corresponds to this piece of the tooth, and another piece of arc there for the top half of the outer part of the tooth, and another one here. So connect these, construction line, that wants to be in the middle. This is 90 degrees. It's going to want to end on this line. Actually, it's going to want to end here. These two are going to be parallel. These two are going to be parallel. This connects here and parallel. These are the same diameter. These are the same diameter. Okay. And then this wants to be a quarter circle. So this wants to be on this line here, which it doesn't like because that's no longer tangent. Yeah, that hasn't worked quite so well. So let's just go back to here. So let's get rid of that constraint that they need to be tangent. That one. No, I didn't want to do that. Curve, curve, tangent. We want to keep that one. Arc, line, tangent. We want to get rid of that one. Right. So that then allows us to bring this down in a more controlled fashion. Now I can put it on and that will work. Again, on this side, we never put on a tangent arc. So I can do that here. Stick that on like so. Now, it's still not right. We want the thing to be symmetrical. So I want this line and this line to be the same length, like so. And in order to position it correctly, I'm going to create a point, stick it on this arc and on this arc. So now we are constrained to places where the point is on this circle here. We want the point to be at the centermost position of this arc. The easiest way to do that is to create a construction line from there to the origin. Nope, from there to the origin, and place this point on that arc. Right, so we now have a completely fixed shape. It is fully constrained, it has no degrees of freedom, and it is a solid shape. So extrude. I don't care about how far it's extruded so far. And now I can, wrong one. Now I can rotate it about this axis and this point. Rotate, change 30. There are too many faces that are flush with each other, and the red lines mean it's having a bit of problem resolving this. I can do that and switch to a different representation that works better. So we should now have a gear. I don't know whether it'll work because the shape of these is different from the pegs in the original shape here. But I believe that my 3D printer will have a much better job of dealing with these than it will with anything longer. Okay, we do need to change how far it is extruded. So we need to come up with a length for this. So we go back to GIMP here and we load this, which I forgot to crop. This is a rather dodgy scan I did of a fragment seen from the side. It's kind of blurred in places because my scanner's depth of field is very poor. I used to have a scanner with really good depth of field. You could put like complete PCBs on it and it would give you detailed in-focus images of everything up to a few centimeters away. But this should be good enough. Let's crop that one more time. Here, select, rotate, show grid. That's more or less horizontal. That should do. I'll crop it one more time. Select like this. I'm just using the selection as a measuring tool to about there and about there, I think. So this is 61 pixels high. So according to our maths, that is 1.29 millimeters thick. So stick a constraint on that line of 1.3. That shrinks a bit, and we now have, hopefully, a properly sized gear wheel. Now this is only part of it. We also need to do the other part. So back into GIMP, and we go to this image. This is the top of the gear wheel, and you can see here these two big cracks. That's from where it was beginning to disintegrate just from handling. So again, crop. Actually, first I need to rotate it. Show grid, rotate. Put the center in the center. And rotate until these two are horizontal. Commit, crop to there and there, and there. Commit, and that has given me an image which is 177 by 178. That's good enough. And I'm going to create a work plane. Actually, hang on, there's one important thing I've forgotten to do. Over here, I can see that there's a 1 under degrees of freedom. That's because I can do this. It might be clearer if there we go. So I haven't actually constrained the angle between each of these wedges. Actually, it's easier to see here. So you can see how I can change the distance between them. In fact, I should be able to put these two corner points. If I do that and that, I now have perspective turned off and I'm looking straight down. So I should be able to tell it that these 2 points should be on top of each other. Right, it can't quite do that because inaccuracies in the algorithm means that it can't put these close enough on top of each other to satisfy the constraints, which is a shame because that's the most intuitive way of doing it. But instead, what I'm going to do is to say that this angle must be the same as this angle must be the same as this angle. I hope that's the right way to do it. Equal angle. Yeah, okay. And that has now popped into position and I now have 0 degrees of freedom. So I want to create a new work plane sitting on top of the gear wheel. So this is our point, which is the top of the wheel. And I'm going to use our original 2 wedge lines to produce the normal. So create work plane, like so. And now add an image, front, and this is going to go on top of this. And as before, we go to GIMP and we see that our image is 177 pixels across. We go over here and we see that that means that it's 3.75 millimeters wide. So this line firstly is horizontal. Secondly is 3.75. So there is our rectangle properly sized, and you can see that the circles do more or less match. We put our construction line across here, as was before. Actually, while I'm working with that, let's just bring it up here. Create a point. Point goes in the middle. And we want that point and that point to be congruent. And there is our reference image placed correctly. And as before, we draw a circle for the inside, which is a construction geometry, and a circle for the outside. And we create a point here and a point here. These need to be on top of each other. These need to be on top of each other. We have a construction line across there. That needs to be a construction line there. That needs to be the same size as that. Set that to construction geometry. Create another construction line from here to here, which is vertical, and from here to I already have that line, so that means the angle between teeth is 45 degrees, which is quite nice. We've created all our construction lines, our reference lines for this gear wheel. So let's create another work plane. There we go. This is yet another layer stacked on top of the others. Hello, why does this say it's got 1 degree of freedom? What can I change? This one. So let's put that there. And I'm just going to see 2.21. Yeah. Let's put a dimension constraint of 2.2 on it to fix it in place. So now it's basically the same process for drawing our geometry. This stuff here is Z order clashing because my reference image here is congruent with the surface of this gear. It's just a reference image, so it doesn't actually matter, but it is a bit ugly. So as is before, create circle of arc like that, circle of arc like that, but 90 degrees, circle of arc like that, put these on top of each other to connect them, that is 90 degrees. This is on this line. This is also on this line. And let's bring this, these two are tangent. And there we go. Because a lot of these shapes, there are two solutions. And Solvespace will sometimes pick the wrong one. It needs a bit of encouragement to get the right one. So these are tangent. This is on this line. This is also on this line. These two are the same diameter. These two are the same diameter. And we should now have our tooth shape. It does say air. Oh, you're right. That's because I don't have a closed shape here to work with. I can handle that easily enough. Create another piece of arc down here. Put that on that line. That on that line. That on the origin. That wants to be on. I have the intermediate steps disabled up here so that this, you can see it highlighting, is our reference circle on the base plane. So we want that and that to be the same diameter, and that gives us our inner circle. So, piece of geometry there. Oh, I pressed the reference geometry button. Piece of geometry there, and the piece of geometry there. And this fills in because it's now, well, filled. And as before, reference geometry from there to there, create a point, put that point on the line, and that has now locked that in the center of our, that's not right. Oh yeah, this and this need to be the same length. There we go. So now I can adjust the inner size of the cog structure. So if I put that point on our inner circle, and I want to adjust this to something sensible. Did I have to do this? No, I didn't have to do that with the other set of teeth. So why? I did put a horizontal constraint across there. So yeah, that'll be it. Okay, piece of reference geometry there to there. Put this on the line. And yeah, that has fixed it in place, but I'm not entirely thrilled because once this has been extruded and rotated, there's actually a concave piece inside, which I don't think I want. So let's just get rid of that. I want this positioned at just such a point so that there is no backward curve here. So I want these curves to be tangent to a line passing through the center point. So if I do that, and I say that this must be tangent, that's worked. Excellent. All right. So there we have our teeth for the inner part of the gear. And apart from the flickering, you can make out that these teeth are actually shorter than the original ones, and likewise these teeth are shorter. But I'm hoping it will work anyway. It will probably need adjustment. But we want to extrude and rotate about this line. And there are 8 of them. There we go. And let's just drag this a bit. Here are our original construction lines. So you want these 2 lines to be the same angle as these 2 lines. Constrain equal angle. And it doesn't quite snap into position. Let's go back to our sketch. And if I select these and put a reference angle on, 44.8. Right. That's not right. Oh, I know what's going on. This is not quite square. Therefore, this line here is not quite at 45 degrees, which is annoying. Okay, let's put another piece of reference geometry there, and want that and that to be actually at 45 degrees. Right. Now, unfortunately, we now have to edit this sketch so that this is attached to the other line. So this points coincident. So that is not actually constrained to be on the line. What about this one? This is the center of this arc here. And right, this is constrained to be on the line. So I delete that constraint. I should be able to drag this. Yeah. Let's put that on this line. That on this line. Like so. Probably here as well. No, those are coincident. Here's our constraint. That point is on that line. There we go. So put that on that one. Right, there we go. And now if I go up to this one, it is still not quite matched, but that's because my equal angle constraint, which is shown here, is referring to the wrong lines. There we go, delete that. This angle to be the same as this angle, equal angle. Bingo. Okay, and back here to GIMP, we look at the side image. I want to know how big this bit is. It's 80 pixels, which is 1.7 millimeters. 1.7. And there is our wedge, which is the right size. We go to the final layer, and here should be our gear. Now, I have no idea whether it works, but the next step is to 3D print it and see. after a lot of work, here is the final product. And here are all the failed prototypes. Let me just move that out of the way. This took a lot of trial and error to make, and I kept having to fiddle with the printer settings on the model. You notice that the original here, in its several pieces from where it has broken apart, has longer teeth than this. In fact, I did have to change the model to make the teeth longer, but if I made them too long, then the gear would just bind and not go round. This seems to be a reasonable compromise where it actually works, although it's not entirely perfect. This is one of the better failed ones. Now, I actually had to buy a 0.2mm nozzle to print this. It's a little hard to see on camera, but printed with the 0.4mm nozzle, the shape of the teeth just aren't right and the gear just doesn't work. As the little motor cog turns, it binds and the whole thing just jams solid. Here's the gearbox unit itself. I have actually tacked a couple of wires onto the motor terminals so that I can make the motor go round. That's running on 5 volts. I don't know if that's the right voltage. It might be a 12 volt thing, but I'm not going to use more than that. So if I place the gear, needs a little bit of, there we go, then it's not exactly quiet, it's quite rattly. That will be probably large tolerances in the teeth, but it does actually seem to work. If I add the second gear, the one that connects it to the rest of the gearbox, and then apply power, it works. I am going to very tentatively add a few drops of light lubricating oil. That should do, because that gear is pretty rough. Let's see what this does. Yeah, that sounds way better. Let's just do one more. The 3D printed part is actually porous. So the oil will get absorbed into the plastic and then released over time. So that should be good. Right, now I just need to put it back together. And there is a small problem with that, which is, this goes on here, which is that the ancient plastic clips have all broken. So this thing is not actually held on by anything other than hopes and prayers. Luckily in the floppy disk drive this goes face down, so it doesn't need to be held on by very much. Once it's installed, it should be fine. So let's just stick a piece of Kaptan tape over it like that. And of course I do need to remove those wires. So now I just need to put this thing back on by first plugging it in, because there is no clearance. And then this thing goes in there. And with luck, that should be all there is to it. So I suppose I'll go and have to try it and see what happens. Fun fact, this cable is not polarized, so I had to look at the pinout to determine which way around to put it. I'm hoping that the stripe on the cable corresponds to pin 1. Anyway, let's try it and see. Power! Well, that wasn't a great noise, but it did do the right thing, so let's try sticking a disc in. Yeah, that noise was horrible, but it does work. Reassembly should be the same as disassembly, but backwards. That just requires me to remember what it was I did. I seem to have 4 screws left over. I hope they weren't important. And here it is, fully functional. And yes, I have figured out where the video memory lives. So that is done. The gear is clearly not perfect. It shouldn't be making that noise. Chances are it'll break sometime in the future. I'll make another one and tinker with the shape a bit. The teeth are clearly not quite right, but it is at least working for now, which allows me to get moving with reverse engineering the typewriter. I hope you enjoyed watching me work Solvespace. I think it's an excellent 3D modeler, and I don't know why other people haven't heard of it. The next job is to fix the keyboard, which is hopelessly ruined by age, but that will be in a different video. So until then, as always, I hope you enjoyed this video. Please let me know what you think in the comments, and I will see you next time.